question seems simple. Is time real? Yet the more you chase the answer, the more it slips away, like sand between your fingers, like light vanishing into the horizon. We live by clocks, measure our days in minutes and years, but what if these divisions are only illusions? What if time is not something we move through, but something our minds create? Tonight, we'll step past the ticking seconds and wander into a universe where time bends, stretches, or disappears entirely. Not to race toward an answer, but to linger in the mystery. Time feels so certain, so woven into the fabric of living, that questioning it seems almost absurd. From the moment you first became aware of the world, you've been carried by it. Birthdays stacking one on another, seasons arriving in sequence, clocks marking the hours between morning and night. It feels less like a thing to believe in, and more like the stage upon which everything else unfolds. But what if the stage is not what it seems? What if the flow you've trusted is not a river at all, but an image your mind has learned to follow? The belief in time's reality is ancient. Early humans read it in the arc of the sun, the waxing and waning of the moon, the return of constellations to the same night sky. Those rhythms were practical guides. When to plant, when to hunt, when to gather. But long before mechanical clocks, there was already an agreement, unspoken yet binding, that there exists something called time that moves forward at a steady pace. In truth, those patterns were never time itself. They were simply change, transformations in the world, in the heavens, in ourselves. Yet our minds turn change into a measurement, and measurement into a reality. From that agreement grew an empire of schedules and calendars. The second became the base unit, carved from the pulse of atomic vibrations. The minute, the hour, the day, each subdivided and stacked with such precision that we could coordinate the flight of spacecraft and the arrival of trains down to fractions of a heartbeat. But all of these measurements, for all their accuracy, depend on something fragile, the assumption that time itself is a universal, unchanging backdrop. Physics has quietly whispered for more than a century that this assumption might not hold. The equations of Einstein's relativity tell us that time is not the same everywhere, nor for everyone. It bends, it stretches, it slows, it speeds, not in ways you can feel moment to moment, but in ways that matter deeply to the universe's structure. A clock orbiting high above Earth ticks differently than one resting in your home. A traveller moving near the speed of light experiences a different span between events than someone who stays behind. This is the first crack in the illusion. Time is not absolute. The same hour can contain different amounts of reality, depending on where you are, how you move, and what gravity touches you. That steady river you imagine is not steady at all. It's a network of twisting channels, each flowing at its own pace. The surprise is not that physics revealed this, but that our everyday lives remain mostly untouched by it. In the grocery store, at the dinner table, between sunrise and sunset, the illusion holds. Why? Because your senses and your mind conspire to make it so. The brain's perception of time is stitched together from signals, rhythms, and changes. It does not see space-time curvature. It does not feel nanoseconds lost or gained at altitude. It presents to you a smooth, continuous flow, an inner metronome that reassures you the world is moving forward at the same rate it did yesterday. This is not a flaw, it's an adaptation. Without it, daily life would be disorienting. And yet, if the flow of time is not fundamental, what is? Some physicists argue that the universe is best described without time at all. The equations that govern quantum fields and relativity can be written in a form where time is not a built-in feature, but something that emerges from deeper relationships, from change, from causality, from patterns that we interpret as temporal. In this view, the past, present and future might all exist in some vast static geometry of the cosmos, and flow is nothing more than the way our consciousness moves through it. This idea unsettles because it threatens the way we make sense of ourselves. If time is not flowing, then what does it mean to age, to remember, to hope? These are not just personal milestones, they're the grammar of existence. The notion that the present is a special, fleeting slice of reality is built into every thought we have. Remove that, and the mind rebels. Yet this rebellion is not unique to you. Every scientific revolution begins with a similar unease, when the map no longer matches the territory. Once, the Earth seemed fixed and the heavens revolved around it. Once, solidity seemed certain until atoms revealed themselves to be mostly empty space. And now, time itself joins the list of things that might not be what they appear. Still, even if time is not fundamental, it remains an extraordinary tool. It orders the events of the universe like beads on a string, allowing us to speak of before and after, to compare intervals, to predict what comes next. In physics, time is the parameter that turns equations into stories. Without it, the laws of motion would be silent. But perhaps it is not the lawgiver we once thought. Perhaps it is the servant, born from deeper truths. Standing at the threshold of this idea, you might feel a kind of vertigo. If the flow of time is an illusion, then you are not moving through moments as much as moments are unfolding in you. Memory is the echo of other coordinates in the universe's grand structure. Anticipation is your mind leaning toward coordinates not yet experienced. The now becomes less a thin slice and more a perspective, like standing on a mountain ridge and seeing both slopes at once. From this vantage, the next question forms naturally. If time is not fundamental, why does it appear so convincingly real? And why does it seem to pass at the same rate for nearly everyone in everyday life? The answer lies in what we use to measure it, the devices and phenomena that stand in for time, but are not time itself. We trust them because they agree with one another, not because they reveal a cosmic truth. This trust brings us to the clock, that quiet authority in your pocket, on your wall, in every corner of civilization. It is our constant companion and judge, slicing the day into perfect segments, reminding us when to wake, when to meet, when to sleep. But in truth, the clock measures motion, not time. The swing of a pendulum, the vibration of a quartz crystal, the oscillation of atoms, all are changes, regular and predictable, but still changes. Without motion, a clock is meaningless, and without a clock, would time exist at all in the same way? The journey ahead will peel back these layers chapter by chapter. We will see how clocks keep us aligned, yet hide the strange flexibility of time itself. We will explore the relativity that lets time bend under speed and gravity. We will follow its one-way arrow and confront the possibility that all moments coexist. And we will ask, again and again, whether the flow you feel is a property of the universe or of the mind that perceives it. For now, hold on to the unease this first crack in the illusion brings. Let it settle beside you like a companion for the road ahead. The seconds you think are passing as you listen may not be what they seem, and by the time we return to this thought, you may never look at them the same way again. We trust clocks the way sailors once trusted the stars, as if they are impartial keepers of truth. A glance at a glowing display tells you when to wake, when to work, when to eat, when to rest. Trains run because clocks agree. Airplanes land because clocks agree. Global trade, science experiments, heart surgeries, all unfold in harmony because of synchronized ticking. But this harmony hides a quiet fact. Clocks do not measure time itself. They measure motion. They count cycles. They tally change. And from that counting, we have built an entire civilization's faith in seconds, minutes, and hours. A pendulum clock swings because gravity pulls on it and inertia carries it through. A quartz clock ticks because a crystal vibrates when voltage runs through it. Atomic clocks, the most precise we've ever made, count the oscillations of electrons as they jump between energy states. Each is regular, dependable, but none is time in its pure form. They are rulers for motion, not windows into a cosmic river. If the motion stops, the clock stops. If the conditions change, so does the ticking. Think of a second, not as an invisible droplet in the stream of time, but as a choice. Humanity made. The modern definition ties it to the vibration of a cesium-133 atom, exactly 9,192,631,770 oscillations. That number is not magic, it's a convention. We might just as easily have chosen the swing of a pendulum, the beating of a heart, or the turn of the earth as our anchor. In fact, we once did. The day, divided into 24 hours, came from the planet's rotation, not from any universal law, but from watching the sun cross the sky. The year came from the Earth's orbit, the month from the moon's cycle. By tying time to motion, we made it something we could measure and share. But we also blurred the difference between the measure and the thing itself. When the Earth slows in its rotation, as it has ever so slightly over millions of years, the day changes length, yet we rarely notice. We simply adjust our clocks, adding leap seconds to keep them aligned with astronomical reality. The flow of time, if it exists independently, doesn't skip or stretch because we changed a definition. Only our count changes. Physics reminds us that motion is local, and so are the measurements that depend on it. A clock on a fast-moving spaceship will tick differently than one on your desk, not because time inside the craft has slowed, but because the processes that make the clock tick are affected by speed and gravity. Two identical atomic clocks, one on a mountain and one at sea level, will disagree after enough days have passed. The mountain clock, feeling less gravity, will tick faster. This isn't a trick of the clock. It's the reality predicted by general relativity and confirmed in experiment after experiment. When you look at a clock, what you see is a tally of events, swings, vibrations, oscillations that happened since a starting point. We mistake the count for an absolute truth. But imagine if nothing moved, nothing changed, no atoms vibrated, no pendulum swung, no hearts beat. Could you still point to time? Or would it vanish, not because it ceased to exist, but because without change there's no way to detect it? That's why many physicists suspect that what we call time is not a fundamental ingredient of the universe, but a reflection of change and relationship. In this view, clocks are translators, converting the patterns of the world into numbers our minds can use. They tell us when, in the same way a ruler tells us how far, by comparing one thing to another. And just as a ruler doesn't create space, a clock doesn't create time. The seduction of the clock is its certainty. When the display says 8 o'clock, you feel as though you've been told a universal fact, something true for everyone everywhere. But 8 o'clock in Tokyo is not 8 o'clock in New York. Even within one city, your clock's reading is only as true as the network it's synced to. Behind that smooth agreement is a constant process of correction. Satellites adjusting for relativistic effects, computers synchronizing over global networks, leap seconds inserted to match Earth's slowing spin. Understanding that clocks are not time is not about making them useless. It's about freeing the mind from mistaking the tool for the thing itself. The second is no more the essence of time than a meter is the essence of space. It's a way of carving the universe into manageable pieces. The deeper question is, does the carving reveal something eternal, or is it just a grid we've laid over something more complex? This realization does not make the clock's face any less familiar, nor the tick any less reassuring, but it invites you to listen differently, not as if you're hearing the universe's heartbeat, but as if you're hearing an echo shaped by human hands, bound to motion, grounded in change. And when we pull at that thread, the illusion begins to unravel. Because if clocks are not time, then what is? And if what we call time is only motion measured, where does the story go when the motion ends? It begins with a simple thought experiment. Imagine you're on a train moving close to the speed of light. You hold a clock in your hand, not a digital one, but a light clock, two mirrors facing each other, with a beam of light bouncing between them. In your view, the light travels straight up and down, ticking off perfect intervals. But someone watching from the platform sees something stranger. To them, the light beam has to travel diagonally, because the train is moving forward. The path is longer, and since light can never go faster than its universal limit, the ticks come more slowly. In your frame, nothing has changed. In theirs, your clock has slowed down. This is the heart of Einstein's special relativity. Time is not absolute. Motion changes its rate. The faster you move through space, the slower you move through time relative to others. This isn't an illusion or a trick of perspective. It is a measurable fact. Time dilation, as it's called, has been confirmed in laboratories with particles moving near light speed. in airplanes carrying precise atomic clocks, and in satellites orbiting high above Earth. In every case, moving clocks run slower when compared to those at rest. Even at everyday speeds, the effect exists, though it's too tiny to notice without exquisite instruments. But push the speed higher, close to light, and the effect grows dramatic. An astronaut traveling at 99.9% the speed of light for what they experience as 1 year might return to find that decades have passed on Earth. For them, the journey was brief. For those left behind, it was a lifetime. Time itself stretched differently for the two observers, not because of mechanical error, but because the universe insists that the speed of light remain constant for everyone, no matter their motion. This constancy is the strange key. Before Einstein, physicists assumed time flowed uniformly everywhere, and that speed simply added together. But experiments, such as the famous Michelson-Morley test, showed that light's speed never changes, whether you chase it or run away from it. To preserve that rule, something else had to give. Space and time themselves had to bend. Lengths contract for moving observers. Clocks slow down. The universe trades between space and time like currency, keeping the balance of space-time intact. Real-world technology depends on this truth. The GPS in your phone relies on satellites circling thousands of kilometers above Earth. Their atomic clocks tick slightly faster due to weaker gravity, a general relativity effect, but also slightly slower due to their speed, a special relativity effect. Engineers must correct for both, or your position would drift by kilometers each day. Without Einstein's equations baked into the system, navigation would fail. In special relativity, there is no single, universal now. Events that are simultaneous for one observer may happen at different times for another moving at high speed. This shatters the idea of a shared cosmic clock. Each observer carries their own time tied to their motion, and yet, in their own frame, their clock always runs normally. You never feel time slowing for you. You only notice it in others who move differently. The thought experiment extends to deep space travel. Imagine a crew heading to a star 20 light-years away at near-light speed. In their frame, the journey may take only a few years, thanks to length contraction. Distances shrink for those in motion. Upon returning, they could find centuries passed on Earth. In effect, they've traveled into the future. This isn't science fiction. It's the logical outcome of nature's rules, demonstrated in particle accelerators, where unstable particles live far longer when moving quickly. Einstein's insight was not to make time exotic, but to make it personal. Each path through the universe, each combination of motion and rest, has its own clock. Space and time are threads in the same fabric, and when one stretches, the other compensates. The speed of light is the loom that keeps the weave tight. When you hear that time slows for something in motion, it's tempting to think of it as a malfunction, as though the moving clock is broken. But the truth is deeper. The laws of physics treat all motion equally. From the clock's point of view, it's everyone else whose time is off. There's no master reference to decide who is correct. Reality is built from this relativity. And so, when Einstein stopped the clock, he didn't destroy the idea of time. He freed it from the tyranny of absolutes. He showed that time is woven into the geometry of the cosmos, that it bends to accommodate the unwavering speed of light, and that your journey through the universe is measured not by a single cosmic rhythm, but by the unique beat of your own motion. From here, the story widens. If motion can slow time, could something else alter it? Could space itself, curved by mass and gravity, make time pass at different rates even without movement? Einstein had an answer for that too, and it would take him beyond the train platform, into the heart of the stars, and to the edges of black holes. Imagine space not as a void, but as a vast, invisible fabric. Every star, planet, and speck of matter presses into it, making dents and curves. This is Einstein's general relativity, the idea that gravity isn't a force pulling objects together, but the bending of space-time itself. Mass tells space how to curve. Curved space tells matter how to move. The planets orbit the sun, not because they are tugged by an invisible rope, but because the sun's mass bends space-time around it, guiding them along curved paths. This bending doesn't just shape where things move, it shapes how they experience time. A clock sitting near a massive body will tick more slowly than one far away. This isn't a flaw in the clock, it's reality itself running at a different pace. Near a massive star or on the surface of a dense planet, seconds stretch. Far from any mass, in the emptiness of interstellar space, they move faster. If you stood on Earth while your twin floated far above, away from gravity's pull, they would age ever so slightly quicker than you. The difference is minuscule in everyday life, but precise enough that GPS satellites must adjust for it. Their orbits place them in weaker gravity, so their onboard clocks tick faster than clocks on the ground. Without constant corrections, your phone's location data would drift by kilometers. Gravity, like speed in special relativity, rewrites the flow of time, but while motion slows time for those in motion, gravity slows it for those deeper in its well. The stronger the gravity, the greater the slowdown. Near the edge of a black hole, this effect becomes extreme. To a distant observer, a clock falling toward the event horizon appears to slow until it nearly stops. Light from the clock becomes stretched into redder and redder wavelengths, gravitational redshift, until it fades from view. For the clock itself, time feels normal. But in the wider universe, its story is almost frozen. Here, spacetime's curvature is so sharp that time and space trade roles. Paths inward become unavoidable, and tomorrow for the falling object never arrives for those watching from afar. This deep connection between space and time comes from the same insight that transformed physics in special relativity. They are not separate entities. They form a single four-dimensional geometry, and mass and energy shape its structure. A planet doesn't just exist in space, it sculpts the stage upon which all motion and all moments occur. Remove the mass, and the stage flattens. Add more mass, and the stage dips further. Even light, which always moves at the same speed, follows these curves. The path of a beam passing near a massive star bends, not because light has weight, but because space itself is bent. This bending was first confirmed in 1919 during a solar eclipse, when starlight passing near the sun was observed to shift from its usual position in the sky. The observation made Einstein famous overnight, a public proof that the fabric of reality could fold under the weight of the cosmos. The practical consequences are everywhere. Without general relativity, our understanding of cosmology collapses. The expanding universe, the behavior of galaxies, the warping seen in gravitational lensing, all come from the rules of curved space-time. Even the birth of the universe in the Big Bang model is described through the stretching of this cosmic fabric. Time itself is woven into these changes, so as space expands, so does the history it contains. On Earth, we rarely feel this curvature because our scale is small. The planet's dent in space-time is shallow compared to stars or black holes. Yet even here, every heartbeat, every sunrise, and every orbit of the moon is choreographed by these invisible curves. We live not on a static stage, but on a sheet that dips and rolls beneath us, carrying time with it. If you could step outside the universe and see space-time laid out as a whole, you'd find it rippling with curves around stars, galaxies, and clusters. Every dip represents a slowing of time, every peak a speeding. And moving from one to another means crossing boundaries where the pace of reality itself changes. This is the essence of general relativity, that the universe is not simply where things are, but when they are, shaped together in a single folding fabric. And so, time is no longer a background tick marking the universe's progress. It is part of the structure, bending with the weight of suns, stretching in the emptiness between them. From here, the next question emerges. If gravity can stretch and slow time, and motion can do the same, what fixes the direction it flows? Why do we always move from past to future, and never the other way around? In every moment of your life, there is a direction you can't reverse. You can stand still or walk forward, turn left or right, even retrace your steps. But you cannot walk back into yesterday. The past is fixed, the future unwritten, and you move from one to the other at a steady, unstoppable pace. This one-way journey feels so natural we rarely question it, but physics demands an answer. Why does time have an arrow? Why do events line up in a sequence we remember in one direction only? At the heart of this mystery lies a single concept: entropy. In the language of thermodynamics, entropy is a measure of disorder, but it is more than just a messy desk or a scrambled egg. It is a deep statistical truth about the universe. The second law of thermodynamics states that in an isolated system, entropy tends to increase. Left alone, order dissolves into disorder. Ice melts into water, smoke disperses into air, and the coffee you stir will never unmix into cream and black again. This law doesn't forbid local decreases in entropy. Life itself builds intricate order, but those decreases are paid for by greater increases elsewhere. The overall balance is always toward more possibilities, more randomness, more ways for particles to be arranged, and that statistical drift toward disorder creates time's arrow. The past is the direction where entropy was lower, the future is where entropy will be higher. Imagine a glass falling from a table. At the moment it shatters, the pieces scatter in countless patterns. The odds of them reassembling into the exact shape they once had are astronomically small. The laws of physics, at the most fundamental level, don't forbid it. They are symmetric in time, but the probabilities make it effectively impossible. That improbability is why we see glasses break but not unbreak, eggs scramble but not unscramble. This is where memory enters the picture. Your mind, like the rest of the universe, is built on physical processes. Memories form as neurons change state, a form of ordering in the brain. Those changes record low-entropy conditions from moments past. But there is no corresponding record of the high-entropy configurations of the future. You remember the past because it is the side of time where things were more ordered, leaving more distinct imprints. The future hasn't happened yet, and when it does, it will be messier. Entropy's growth is tied to the expansion of the universe itself. In its earliest moments, just after the Big Bang, the cosmos was surprisingly uniform, hot, dense, and smooth. That smoothness was low in gravitational entropy, even though it was full of energy. Over billions of years, gravity has pulled matter into clumps, stars, galaxies, planets, increasing complexity but also increasing the total number of possible states the universe could occupy. With every passing second, the overall entropy climbs. You can think of it like a deck of cards. Perfectly ordered, the deck has low entropy. Shuffle it, and the number of possible arrangements skyrockets. The universe began like a freshly ordered deck. Time's passage is the shuffle. Each moment, the arrangement grows less special, more statistically common. The beauty of entropy is that it doesn't require a clock. You don't need to measure seconds to know which way time is moving. Just look for the direction in which disorder increases. The melting of ice, the spreading of heat, the fading of a scent in the air, each is a small compass pointing along time's arrow. But here is the strange part. The fundamental equations of physics, Newton's laws, Maxwell's equations, quantum mechanics, don't prefer one direction of time over another. They work just as well run backward. If you watched a planet orbiting a star in reverse, the math would still hold. The arrow of time emerges not from these equations, but from the conditions the universe began with. The low entropy start gives us the asymmetry we live inside. This realization opens unsettling possibilities. If the universe had begun in a high entropy state, there would be no arrow of time. Events would look the same forward and backward. Without an arrow, there would be no meaningful before or after, just a static, changeless reality. The fact that we experience time flowing is a clue about the special nature of the cosmos's beginning. Some physicists speculate that entropy might eventually reach a maximum, a heat death, where the universe becomes a thin, uniform bath of particles and radiation. In that far future, with no gradients left to drive change, the arrow of time could lose its meaning. The universe would still exist, but nothing would happen. Others imagine cycles where entropy resets in a new Big Bang, birthing another low-entropy beginning. In your everyday life, entropy works quietly but relentlessly. You tidy a room, but dust returns. You fix a machine, but wear and tear creep in. Even your own body resists the inevitable for decades, repairing damage, replacing cells, yet the balance tips toward disorder in the end. The arrow of time is not just cosmic, it is personal, and yet within this rule lies a kind of beauty. Every memory you hold exists because the universe was more ordered a moment ago. Every photograph, every fossil, every ancient starlight we see across the cosmos is a frozen record of lower entropy, a trace of the path we've taken. Entropy writes history into the structure of reality. Without it, there would be no story, no sequence, no life. The arrow that points from past to future is not painted onto the surface of time. It emerges from the way matter and energy arrange themselves, from the improbable beginning we were given. And it is this arrow that leads us to the next great question. If time has a direction, what does that mean for its full shape? Is the future being created moment by moment, or does it already exist alongside the past, waiting for us to arrive? From the moment we first learned about the Big Bang, we've been told it was the ultimate starting point, a flash of creation, a cosmic curtain rising on space and time. But what if it wasn't the beginning at all? What if time itself stretches far beyond that moment, into a past without edges, without a first heartbeat? The idea is unsettling. Our minds are built to think in stories, and every story has a first page, but the universe may not, and that changes everything we think we know. For centuries, the human timeline has felt reassuring. We like origins, a first dawn, a first cause, a place where we can say, here it all began. Ancient myths told of gods forging worlds, of skies split open, of the first light. Modern science replaced those myths with equations and telescopes, but kept the same instinct, the Big Bang as our cosmic day one. Yet physics whispers that this beginning may just be the start of our local chapter, not the book itself. A chapter set inside something far older, perhaps something eternal. To understand this, we have to look at what the Big Bang really means. It's not an explosion in space. It's space itself expanding from an incredibly hot, dense state. Go far enough back in time and all distances shrink, all matter compresses, until the equations break down in a singularity. But that singularity may be less like a wall and more like a fog bank. Not the end of the road, just the point where our current map stops working. What lies before could be another stretch of time, perhaps infinite. Some physicists imagine a cyclic universe, where Big Bangs are not unique events, but recurring pulses in an endless heartbeat. Expansion gives way to contraction, which collapses into a new bang, and the cycle begins again. In such a cosmos, time has no starting point, only patterns repeating across eternities. We might be living in the 1000th iteration, or the millionth, with entire epochs erased behind us, their stars long gone. In this view, the universe doesn't have an age, only the current cycle does. Other models push the beginning even farther away by asking if time could emerge from something timeless. Quantum cosmology proposes that before the Big Bang, the universe may have existed in a quantum state where time had no meaning at all, a sort of frozen potential. Then a quantum fluctuation could have sparked expansion, and with expansion came the ticking of cosmic time. From that moment on, we could measure past and future. But the timeless state before, it might still exist beneath it all, unchanged. And then there's the possibility of a multiverse, not just infinite space, but infinite time as well. Imagine countless universes bubbling into existence, each with its own timeline. The Big Bang we know could be just one bubble's beginning, while others formed long before ours, and still more will form long after. Time in such a framework doesn't start or end. It's simply an unbroken expanse where creation is always happening somewhere. These ideas can feel dizzying because they force us to let go of the safety of a clear start. If time has no beginning, there's no ultimate origin story, no moment where nothing became something. But perhaps that's the wrong way to think about it. In physics, nothing is rarely truly empty. Even in a vacuum, quantum fields hum with energy. Space itself is restless, never completely still. In such a reality, the transition from before to now may be less about creation and more about transformation. The challenge comes in testing these ideas. We can't observe before the Big Bang directly, because the early universe erased its own history. The hot plasma that filled the cosmos in its first 380,000 years was opaque to light. Only after it cooled could photons travel freely, giving us the cosmic microwave background we see today. That background is a kind of horizon. Beyond it, we can only infer using mathematics and the faint fingerprints those earlier conditions left behind. Still, the universe offers hints. Tiny variations in the cosmic microwave background, the slight differences in temperature across the sky, may carry clues about the conditions before expansion. Some patterns might hint at a bounce from a previous universe, or ripples from interactions that happened before our time began. If future observations confirm them, we may have evidence that time extends beyond the Big Bang. Even without direct proof, our equations leave the door open. General relativity describes how space and time behave on large scales, but it doesn't forbid an eternal past. Quantum mechanics governs the microscopic realm, and when the two are combined in attempts at quantum gravity, new possibilities emerge. Possibilities where time is more flexible, where beginnings and endings dissolve into a wider continuum. If we accept that time might not have a beginning, we face deeper philosophical questions. In an infinite past, every event, no matter how improbable, could happen somewhere, sometime. Patterns could recur, histories could echo, and perhaps even versions of us could arise again and again. It's a strange mirror to look into. A universe without origin also means a universe without ultimate finality. But it also humbles us. Our own lives are tiny arcs inside a vast line that may have no ends. Every moment we experience is shaped by a history that may stretch back without limit, a chain of causes reaching into a fog we can't penetrate. We are not at the center of time. We are simply part of its flow, whether that flow began or not. And perhaps that's the most unsettling truth of all. We may never know for certain. The beginning of time could be forever beyond our reach, not because it doesn't exist, but because the nature of time itself prevents us from seeing it. We are bound within its current, measuring changes, watching days and years unfold. But the source of the river may be lost in an infinite ocean. Yet there's beauty in this mystery. If time has no beginning, then it is not a fragile thread that can be cut, but a sea in which all things swim. The stars, the galaxies, even the moments we hold dear, all part of a continuum that needs no origin to be real. In such a universe, the question, when did it all begin, becomes less important than what is happening now and what will come next. From here, we move toward a different kind of frontier, one inside our own minds. If time's beginning is unknowable, then perhaps the only time we can truly know is the one we carry within us. In the next chapter, we leave the vastness of cosmic history and turn inward to see how the human mind manufactures time, stretching and shrinking it, bending it in ways even the universe might envy. Time, as the universe tells it, is measured by the steady beat of physical events, planets orbiting stars, atoms vibrating, light crossing space. But the time inside your mind is a different creature. It stretches and shrinks, hesitates and races, bends around memory and attention. A minute on the clock may be constant, but a minute in your mind is elastic. In moments of fear, it swells until each heartbeat feels separate. In moments of boredom, it collapses into nothing. You don't just live in time, you make it. This is not poetry. Neuroscience shows that your brain does not have a single master clock, ticking away like a metronome. Instead, it has a network of systems, some tied to your senses, others to your memory, others to your emotions, each tracking duration in its own way. The feeling of now emerges when these systems align. When they don't, time warps. A second can seem endless. An hour can vanish. One of the most powerful shapers of time is attention. When you focus intensely on something new, your brain floods with sensory detail. Each sound, each shift in light, each micro-expression is recorded. Later, when you recall that moment, the sheer density of memories makes it feel longer. This is why the first days in a new city feel spacious. Your mind is capturing everything. But as the days settle into routine, your brain stops storing so much. A week can pass, and it feels as though nothing happened at all. Emotion is another sculptor of time. In danger, your amygdala, the brain's alarm system, kicks into overdrive. It boosts the flow of sensory information to your memory centers, making each instant feel hyper-real. People who survive accidents often say it was like time slowed down. The reality is that perception sped up. Your brain was writing more frames into each second, like a high-speed camera. On the other hand, when you're deeply at peace, the opposite happens. Time flows in a smooth, unbroken stream, without sharp edges. Minutes merge into hours without your noticing. Memory plays its own tricks. The length of an experience in memory is not decided by its duration, but by the number of changes your brain recorded. A long, uneventful afternoon can collapse into a single mental snapshot. A brief but intense encounter can occupy a large space in memory. This is why childhood summers feel endless when you're in them. Every day is new, every moment is change, but seem compressed when you look back decades later. Even your body has timekeepers. Your circadian rhythm, set by light-sensitive cells in your eyes, anchors you to the 24-hour day. Shorter rhythms, ultradian cycles, govern your alertness and fatigue in spans of about 90 minutes. Your heartbeat sets a subtle rhythm for your perception, and some research suggests you unconsciously use your pulse as a timing reference. Disrupt these rhythms, and time itself feels unstable, as anyone who has flown across time zones or worked night shifts knows. And then there's the role of prediction. Your brain is not just a recorder, it's a forecaster. It constantly predicts what will happen next and when. If reality matches prediction, your sense of time remains steady. If it doesn't, if something unexpected happens, your brain takes longer to process it and the moment expands. This is why a sudden surprise can feel slowed, and why monotony, which matches your predictions perfectly, can feel like no time at all. Technology has begun to exploit this. Fast-cut videos and rapid scene changes can make a short clip feel longer because your brain has to process more transitions. Slow, unbroken shots can make long sequences feel shorter. Even in daily life, switching tasks frequently can give the impression of a longer day, while deep, uninterrupted focus can make hours disappear. But the most profound distortions happen when memory and attention meet. Think about the way nostalgia changes time. A song from years ago can drop you back into a moment so vividly that the years between seem to vanish. Conversely, moments of grief can stretch into what feels like forever, because the mind cannot stop replaying them, re-engraving them into memory. In both cases, the clock on the wall is irrelevant. The clock in the mind has taken over. We can even manipulate our own time perception deliberately. Mindfulness practices slow the sense of time by heightening attention to the present, the opposite of letting moments blur into routine. Flow states, the deep immersion of an athlete, artist, or scientist in their work, compress time, creating the feeling of losing yourself for hours. Both states are valuable, even though they bend time in opposite directions. This plasticity of time perception is more than a curiosity. It is a survival trait. For our ancestors, the ability to slow time in a crisis meant more chances to react and survive. The ability to compress uneventful days meant conserving mental energy for when it was needed most. But in our modern world, where crises are rare but routines are constant, these same mechanisms can make life feel either too short or unbearably long. Perhaps the strangest implication is that your now is never truly now. By the time sensory information reaches your consciousness, a fraction of a second has already passed. Your brain stitches together inputs from different senses, each traveling at different speeds, into a seamless moment. That moment is already in the past, but you experience it as the present. In a sense, we are all living slightly delayed lives. This gap, tiny but constant, is a reminder that even within our own minds, time is not a fixed flow. It is a construction, rebuilt moment by moment. The seconds of a clock are real in physics, but your seconds are personal, colored by attention, emotion, and memory. They can never be exactly the same as someone else's. And so, when you look back on your life, you are not remembering the time that truly passed. You are remembering the time your mind manufactured. The childhood summers, the first loves, the moments of fear, the days that disappeared, all stitched together into the story of a life. Physics can measure duration, but only you can feel it. At the human scale, time feels like a steady river. Seconds marching forward, never pausing, never skipping. Even Einstein's relativity, with its bending and slowing, still treats time as a smooth fabric. But at the smallest scales of nature, deep in the quantum world, that river begins to dissolve into mist. The flow becomes uncertain, jittery, and in some interpretations, it might not exist at all. The idea of a universal clock, one ticking rhythm for all of reality, begins to crumble. To reach this fog, you must shrink your view down to atoms, then smaller still to electrons, quarks, and the vacuum fields beneath them. Here, the neat predictability of classical physics gives way to quantum mechanics, a domain ruled by probability. The question, what time is it, becomes slippery because events do not always have a clear order. The before and after we take for granted can blur into something stranger. One of the core principles of quantum mechanics is that particles do not exist in single, definite states until they are measured. Instead, they live in superpositions, multiple possibilities layered together. If position can be indefinite and momentum can be indefinite, could time itself also be indefinite? Quantum theory suggests yes. At the Planck scale, the unimaginably tiny length of 10 to the negative 35th power meters and the Planck time of 5.410 to the negative 44th power seconds, 10 to the power of negative 43, 10 to the power of negative 43, 10 to the power of negative 43 seconds. Our familiar concept of continuous time stops making sense. The mathematics breaks down. The smooth line of time may, at its foundation, be grainy, like a film made of discrete frames. Physicists have tried to unite quantum mechanics with Einstein's relativity into a single theory of quantum gravity. In doing so, they've stumbled upon an unsettling possibility. The equations don't require time to exist as an independent variable. In some formulations, such as the Wheeler-DeWitt equation, time drops out entirely. The universe, at its most fundamental level, may be timeless. What we call time might emerge only when large-scale patterns, stars, atoms, even conscious observers, create a way to measure change. But if time is emergent, what is it emerging from? Some researchers propose that it comes from quantum entanglement, the deep connection between particles that share information instantaneously, regardless of distance. In this view, before and after are not baked into the universe but arise from correlations between states. When enough of these correlations link together, they create the appearance of a flowing clock. Without them, there is no now. Experiments have begun to test this. In certain quantum systems, researchers can arrange events so that their order is undefined. One does not happen before or after the other in any absolute sense. This phenomenon, called indefinite causal order, is more than a thought experiment. It can be realized using photons in special interferometers, where the photon's path places two operations in a quantum superposition of orders. At that level, the arrow of time is not fixed. It is a probabilistic haze. This quantum ambiguity might also explain why time behaves differently for particles and systems. Isolated quantum particles can evolve forward and backward in their equations of motion with equal validity. The fundamental laws are time symmetric. The universe at this scale does not distinguish past from future. The irreversible arrow of time tied to entropy only appears when large numbers of particles interact, creating statistical irreversibility. In other words, the sensation of time's direction is a property of the macroscopic world, not a fundamental law of the microscopic one. There's another twist. Quantum theory hints that the vacuum of space is not empty. It seethes with virtual particles flickering in and out of existence, each with lifetimes so brief they defy the ordinary sense of duration. This restless activity may be the quantum origin of the ticking we perceive at larger scales. But here, the tick is not regular. It is noisy, unpredictable, and perhaps more like static than a metronome. If time is not continuous but comes in quanta, discrete packets, it would revolutionize physics. Some approaches to quantum gravity, like loop quantum gravity, predict precisely that. Time is quantized, with the smallest possible interval being the Planck time. No clock could ever measure anything shorter, not because of technological limits, but because such instants do not exist. Between one Planck tick and the next, there is no in-between. But there's a deeper implication. If time has no meaning at the most fundamental level, then the universe's story is not a sequence of events. It's a complete static structure. From our embedded perspective, moving through slices of this structure, we experience change. But outside of that perspective, the whole exists all at once. In this sense, the quantum world and the block universe picture from Relativity converge. Reality contains every moment, but our awareness moves through it like a beam of light scanning a film strip. Some theorists have even suggested that time might be an illusion created by quantum measurement itself. In this view, it is only when we interact with a system, forcing it into a definite state, that we can define before and after. Without interaction, the universe has no preferred direction and no clear flow. That would make time a byproduct of information exchange, a side effect of observation. For now, these ideas remain partly speculative, because probing the quantum structure of time is extraordinarily difficult. Our best atomic clocks, which use the vibrations of cesium or strontium atoms, can measure time to within 1 second over the age of the universe, yet they still operate far above the Planck scale, where the deepest mysteries lie. Reaching that scale may require a new kind of physics entirely, or clever experiments that use astronomical observations, like the timing of high-energy photons from distant gamma-ray bursts, to search for signs of discrete time steps. Still, even without final answers, quantum theory forces us to confront a strange truth. The ticking of the universe is not the same everywhere, and at the smallest scales it may not tick at all. The quantum fog at nature's foundation may hold no clocks, no arrows, no flow, just a web of relationships, from which time emerges only when we step back and look at the bigger picture. And so, the universal clock we imagine, one that beats the same in every corner of the cosmos, is a comforting fiction. The reality is subtler, stranger, and perhaps more beautiful. Time in the quantum fog is not something the universe has. It is something we find when we look at it in a certain way. There are places in the universe where time itself seems to falter, places where the equations we trust begin to tremble, and the neat flow of seconds stops making sense. Here, the clock's hands freeze, not because they break, but because time, as we know it, no longer exists. These are the frontiers where the universe reveals its most unsettling truth. Time is not guaranteed. One of those frontiers is the edge of a black hole, the event horizon. Imagine falling toward it. From your perspective, nothing unusual happens at first. You drift closer, pulled by gravity so strong it bends light itself. But to a distant observer, watching you fall, something strange begins. Your motion slows. Each signal you send takes longer to arrive. Your voice, your heartbeat, even the light reflecting from your skin, shifts to deeper and deeper red. Then it fades entirely. You never seem to cross the horizon. You freeze in place, suspended in time. This is not an illusion. Einstein's general relativity tells us that gravity does not just pull on matter, it pulls on time. Near a massive object, clocks tick slower. Near the event horizon of a black hole, that slowing becomes infinite. A second for you might stretch into billions of years for the outside universe. From their perspective, you never arrive. From yours, you pass through the horizon normally, but you carry your own private time into a place from which no signals return. What lies beyond that horizon is still hidden from physics. Our equations, so precise and tested, collapse under the extreme curvature of spacetime. The densities approach infinity. The very concept of before and after may not apply. Inside, time might flow toward a singular point, where all paths end and causality itself dissolves. Yet black holes are not the only places where time can disappear. To find the other, you must travel backward, not in space but in history, to the very first moments after the Big Bang. The further you go, the hotter and denser the universe becomes. At about 1 second after the beginning, nuclei form. At a microsecond, quarks and gluons roam freely in a cosmic soup. At a trillionth of a second, forces unify. Beyond that, to the Planck time, 10 to the negative 43rd seconds after the Big Bang, our theories no longer work. Time itself might not exist in any meaningful sense. In those earliest instants, the universe may have been in a quantum gravitational state. No familiar space, no steady clock. Some physicists suggest that asking what happened before is meaningless, because before is a concept that only applies when time exists. The Big Bang in this view was not an explosion in time, it was the creation of time. There are also models that imagine time looping, bouncing, or emerging from a timeless sea. In cyclic cosmologies, a previous universe collapsed, rebounded, and gave birth to ours. In emergent time models, the universe existed in a timeless phase before transitioning into one with a measurable flow. In both, the moment of transition marks the daytime, as we know it began, and perhaps the day it could vanish again. Even in the modern universe, there are hints that time stability might be fragile. In certain extreme conditions, near neutron stars, in high-energy particle collisions, or deep inside quantum experiments, the rules governing time's flow can stretch and twist. At the quantum scale, before and after are not always absolute. At the cosmic scale, gravity can slow or even freeze the ticking of clocks. These two extremes, the smallest and the largest, are where physics still searches for answers. Consider the fate of an astronaut falling into a supermassive black hole. If they could survive the crossing of the event horizon, their journey would end at the singularity in finite personal time. But for the universe outside, that fall would never complete. Billions of years might pass. Stars would die, galaxies would fade, and still, the moment of their arrival would remain forever out of reach. In that split reality, time has different meanings for different observers. Now imagine the reverse, the universe's first trillionth of a second. Space was expanding faster than light, driven by a brief inflationary burst. Quantum fluctuations in that inflation laid the seeds for galaxies, but the idea of a clock ticking through that phase is tricky. The expansion rate was so extreme that conventional measures of time break down. There was no external frame to compare against, no stable rhythm. The duration of inflation may not be something we can define at all. The connection between these extremes, black hole interiors and the Big Bang, is one of the deepest mysteries in physics. In both cases, time as a meaningful dimension seems to end. Some theories suggest that they might be the same phenomenon in different guises. The Big Bang could be the inside of a black hole in another universe, and every black hole in our universe could birth new universes on the other side of their singularities. In such a framework, time doesn't truly vanish. It transforms, slipping into another branch of reality beyond our reach. But for those trapped on our side of the horizon, the daytime disappears is final. In relativity, that moment is absolute for the traveler and forever inaccessible to the outside. In cosmology, the moment before time existed is locked away, beyond even light's ability to return. These are boundaries not just of space, but of understanding. And yet, the possibility that time can fail is not a cause for despair. It is a window into a deeper truth. Our familiar seconds, minutes, and hours are local conditions, not universal laws. They emerge from the way space-time behaves under ordinary conditions. Change the conditions enough. Warp space-time with enough mass. Compress the universe into enough density, and the very machinery that produces time breaks. This has philosophical weight as well as physical. If time can vanish, then our stories, our cause and effect reasoning, and even our idea of progress are tied to a fragile feature of the cosmos in a timeless state. Past and future lose meaning, and all that exists is a kind of eternal everything. Some thinkers call this the ultimate reality, a place where all events coexist and the flow of time is a property only minds like ours experience. One day, far into the future, The universe itself might face such an ending. If cosmic expansion accelerates without limit, galaxies will drift apart faster than light, stars will burn out, and matter will decay. Eventually, only a thin soup of particles will remain, scattered so far apart that interactions become impossible. In that cold, empty state, without change or events, time will have nothing left to measure. It will fade, not in a sudden halt, but in a long dimming, like the last echo in an infinite hall. The end of time does not have to be dramatic. It can be quiet. It can be the moment when nothing else changes. In black holes, it happens at the horizon. In the early universe, it happened before clocks began. And in the far future, it could happen everywhere at once as the universe slides into stillness. The daytime disappears is not a single date on a calendar. It is a condition, one the cosmos has met before and will meet again. It is the edge of physics, the place where our equations lose their power and our imagination must step in. To understand it fully, we may need a theory that merges quantum mechanics and relativity, uniting the smallest and the largest into one coherent picture. Until then, we can only circle these edges, aware that somewhere beyond them, time itself is not welcome. It is tempting to think of time as the most fundamental thing there is, the canvas upon which all events are painted. But what if the canvas isn't really there? What if time is not a basic ingredient of the universe at all, but something that emerges, like a rainbow appearing only when light meets water? Some of the deepest equations in physics whisper this possibility. When Einstein's general relativity is combined with quantum mechanics in certain forms, time vanishes from the math. The Wheeler-DeWitt equation, proposed in the 1960s, describes the universe's quantum state without a time variable at all. The equation simply says the universe is, not that it evolves. To extract our familiar ticking seconds from such a framework, physicists must find a way for time to emerge as an approximate description, much like temperature emerges from the random motion of atoms. This is where the idea of emergent time comes in. In this view, time is not built into the foundation of reality. Instead, it arises from the relationships between changing things. Without change, there is no time. And without things to compare change against, there is no flow. Imagine a book containing every frame of a movie stacked together. The story only plays when someone flips through the pages. The flipping is not part of the book. It is an act of perception. Could our universe be like that book, all moments coexisting, and what we call time simply the mind's act of moving through them? Some theories push this further, suggesting the universe itself is like a hologram. In the holographic principle, all the information describing a volume of space could be encoded on a lower dimensional surface, much like a 3D image encoded in a flat sheet of holographic film. In such a framework, our experience of time could be a projection, emerging from timeless patterns in this underlying reality. The before and after we experience might be nothing more than ways our brains order events in a pattern that makes sense for survival. Neuroscience adds another twist. The brain has no single master clock. Instead, it stitches together inputs from many different processes: light signals from the eyes, rhythms from the inner ear, chemical pulses from neurons. These are integrated into a seamless flow, but the flow is constructed. It is not given. When the brain's rhythms shift, as in moments of danger or deep meditation, our sense of time shifts too. This suggests that time as we experience it is not a direct readout of some cosmic metronome. It is an interpretation, a story the brain tells. Some physicists take this seriously enough to argue that the flow of time is entirely a human construct. The block universe model, for example, sees past, present, and future as equally real. In this view, all events exist simultaneously in a four-dimensional spacetime. The passage of time, the sense that we are moving from past to future, is a feature of consciousness, not of physics. From outside the block, nothing moves. But if time is an illusion, why does the illusion have such consistent rules? Why do we all agree on sequences of cause and effect? One possible answer comes from quantum mechanics. At the smallest scales, events are not strictly determined. They are described by probabilities. Yet when many quantum events combine, a stable pattern emerges. Time could be a macroscopic phenomenon, like a river's current emerging from countless chaotic water molecules. The molecules don't flow in the same way the river does, but taken together, a direction appears. Other approaches point to entropy, the measure of disorder, as the source of our time's arrow. In the laws of physics, most processes work the same forward or backward in time, but entropy tends to increase, giving us a preferred direction from order to disorder. Without entropy's steady climb, there might be no distinction between past and future. This suggests that what we call time may be nothing more than the unfolding of entropy in a particular universe with particular conditions. The possibility that time is emergent also appears in attempts to unify quantum mechanics and gravity. Loop quantum gravity, for example, proposes that space-time itself is made of discrete building blocks, like atoms of space and time. In such a framework, what we perceive as a smooth flow is really the large-scale behavior of countless microscopic interactions, just as a smooth surface hides the graininess of its underlying structure. If that's true, then at the deepest level, time may be granular, and between those grains it might not exist at all. This can be hard to accept, because our lives are so anchored in time's apparent reality. We age, we remember, we anticipate. Our language and our thinking are built around before and after. To say that these distinctions might not be fundamental feels like saying the ground beneath us is not real. And yet, history shows that our intuitions are not always reliable guides to the universe's true nature. We once thought Earth was stationary, the sun was eternal, and space was flat. Reality turned out to be stranger and more beautiful than those early assumptions allowed. If time is an illusion, it does not make our experience of it any less important. Illusions can be powerful, shaping how we act and what we value. The sunrise is an illusion. Earth turns, not the sun. But the beauty of dawn is real to us. The solidity of a table is an illusion. It is mostly empty space between atoms, yet it holds our weight. Time could be like that, not fundamental, yet deeply real in the human sense. There's also the possibility that time's reality is conditional. In certain extreme environments, near black holes in the early universe or at the quantum scale, the illusion might break down, revealing a different kind of order beneath. That would explain why our everyday physics works so well here on Earth, but fails at the boundaries of the cosmos. Our sense of time might be a local adaptation, like eyes evolved to see only a narrow band of the electromagnetic spectrum. There may be other modes of reality that we simply cannot perceive. Philosophers have wrestled with this for centuries. Augustine of Hippo, writing in the 4th century, confessed that he understood what time was until someone asked him to explain it. The question has not grown any easier. If the universe is timeless at its core, then everything we experience as change may be a kind of mental map of a changeless territory. And yet, the mystery remains open. No experiment has yet shown us a reality without time, though hints keep appearing at the edges of physics. Perhaps the final theory of the universe will reveal that time is indeed emergent, like temperature, color, or sound, real in context, but not woven into the ultimate fabric of existence. Or perhaps we will discover that time, though mutable and strange, is more fundamental than we can yet see. It begins in quiet. The kind of quiet that doesn't simply mean the absence of noise, but the kind that settles inside you, loosening the threads you've been holding tight. You've walked with time in so many disguises, ticking clocks, curving space, slowing, light, moments stretched and moments lost, and each time you thought you'd seen its face, it shifted. Now, standing here at the end of the journey, you begin to understand. The question was never just, what is time? The question was always, how do you live when its edges blur? The scientists, poets, and dreamers who've looked hardest into this mystery often return with the same confession. We don't know if time exists the way we think it does. Our equations can be written without it. Our quantum theories whisper that it might only be a side effect of change, a convenience born from motion. The block universe tells us that every moment is already here, waiting, unchanging, yet we only ever feel one. And still, Life unfolds as though there were a great river pulling us forward, even if the water is only an illusion in the mind. Perhaps the truth isn't meant to be caged in a single answer. Physics offers models: space-time curvature, thermodynamic arrows, quantum indeterminacy, but none can wrap around the whole. Philosophy offers language, eternalism, presentism, growing block, but language itself is woven with tenses, a net that sags when pulled into the deep. We live in metaphors because the reality is too large for direct touch, and maybe that's all right. Not knowing doesn't close the door, it opens it wider. If the universe does not have a single, universal clock, then every heartbeat, every sunrise, every revolution of Earth is a private measure. On a distant world circling another sun, time might move at a different pace. Near a black hole, it would nearly stop. And yet for those who live in those frames, nothing feels strange. They are simply in it. That's the strange comfort of relativity. It tells us that there is no master time, only yours and mine and theirs, each one complete in itself. From this perspective, the urgency we feel, the pressure to keep pace with the ticking, softens. If time is not absolute, then neither is the race against it. We can choose to fill our present not because it's slipping away, but because it's here now, and now is all we ever truly inhabit. The future is a story not yet told. The past is a library we can visit, but never rewrite. The present is the only page we can touch with both hands. In the cosmic view, life is the flicker of a candle in a vast dark, a brief pattern in the great arrangement of matter and energy. In the intimate view, life is the warmth of a breath, the sound of rain against glass, the shared glance across a crowded room. Both are true. Time's mystery holds them together without contradiction. It is both endless and fragile, impersonal and deeply personal. And so we return to the question of living. If time's reality is uncertain, if its flow is subjective, if the clock on your wall is not the same as the clock in your cells, then how should you meet it? Perhaps the answer is to stop trying to measure every second and start inhabiting them. 2. Understand that wasting time is only real if you believe there is a single correct way to spend it. That joy, rest, and wonder are not gaps in productivity. They are the moments that give the rest meaning. Every ending, too, is softened by this view. If the block universe is right, then nothing is truly gone. Every laugh, every goodbye, every sunrise is still there, in its own coordinate in space-time, untouched. If time is emergent, then perhaps the universe is making the story as it goes, and endings are simply pauses before a new rhythm begins. Either way, the grief of passing is held within a larger frame, one where nothing is lost, only transformed. And here you are, at the last chapter, not at the end of time, but at the edge of what we've been able to follow together. The equations can't take us further. The metaphors begin to collapse under their own weight. All that remains is the awareness that you are part of it, not just moving through time, but making it, shaping it, experiencing it in a way no one else ever will. Your timeline is yours alone, even as it's stitched into the great fabric we all share. So you step forward, carrying the questions rather than the answers. You watch the hands of the clock move, knowing they're not time, but still loving their rhythm. You wake each morning into a present that is always new, whether or not the universe thinks so. You walk beneath the stars, some of whose light began its journey before Earth had oceans, and you feel the connection across centuries, across illusions, across everything we still do not know. And as you live, fully, imperfectly, briefly, you begin to see that the mystery was never an obstacle to understanding. It is the understanding. The uncertainty is not a crack in the truth. It's the space where wonder enters. And in that space, life becomes not a countdown, but a canvas, painted in moments you'll carry forever, in whatever form forever turns out to be.